In this video, we will continue the discussion of proton NMR. So this is proton NMR part 2, and we'll dial in on the unique sets of hydrogens aspect of the key information that the NMR spectra can give you. All right, so we'll review that. We'll look at the number of signals in the proton NMR spectra based on that. I'll go over a heavy atom replacement test. I like to call it the deuterium replacement. And then also you can determine how many or the types of protons available in a structure based on rotational or reflectional symmetry on whether or not they're going to be NMR equivalent or not. So any proton that is similar to another by rotation or reflection then is NMR equivalent to that other proton. All right, so once again, the number of equivalent sets of hydrogens will correlate to the number of signals that you see in the NMR spectra. And that's all we're going to focus on in this video. The other components here, they have their own video as well. So identifying the non-equivalent hydrogens, the number of signals in the proton NMR spectra, as I already mentioned, indicates the number of unique sets of protons in the structure. So protons that are in a set are unique to other sets, okay? But the protons in the set are all NMR equivalent, which is why they're all giving rise to that signal, okay? So protons in different chemical environments can give rise to different signals, and that's what you're seeing in the NMR. So NMR equivalent or chemically equivalent protons occupy identical or mirror imaged environments will produce identical signals in the proton NMR. Chemically non-equivalent protons are not NMR equivalent, and so they do not occupy identical or mirror imaged environments and will produce their own signal. In theory, these will also have different chemical shifts. However, sometimes peaks can overlap with one another. So you may have two sets of unique protons that, in terms of functionality, they're pretty similar and they might have similar chemical shifts, and those chemical shifts might overlap. So it appears as if it's one signal, but when you look at the structure, then you can infer back to the knowledge of what we're talking about here. Are they in theory different? Should they in theory give their own signal? And usually the NMR peaks are pretty well resolved when they're part of completely different functional groups, okay? Because different functional groups have completely different chemical shifts. Chemically equivalent protons or groups are called homotopic or enantiotopic. Homotopic are interchanged by rotational symmetry. So if you close your eyes and you flip the molecule over, you will not have known anything happened, all right? Because it's hard to see the difference because they're identical. Enantiotopic protons, these are interchanged by reflectional symmetry, but then also by configurational changes when we do this heavy atom test that I'm going to show you. It's essentially a foolproof way to figure this out. And then chemically non-equivalent protons, these are pretty easy to spot, and they necessarily don't even require you to do anything further, but these are diastereotopic protons, or these are just protons that look different to the eye. They're connected different, they have different connectivity, so they're called heterotopic. Okay, so chemically equivalent protons are homotopic and enantiotopic. Chemically non-equivalent are diastereotopic and heterotopic. So let's look at a test here. This is going to be a qualitative test for proton equivalency, and we're just going to evaluate the topicity of the proton. I like to use deuterium, so I call it the deuterium replacement test. It's very easy to do. And what it basically requires you to do is the following. For a pair of protons to be tested, replace one and then the other separately with a heavier atom. So I'll just use deuterium, since deuterium technically is one mass unit higher than hydrogen. And then you compare the two structures that you're forming. side by side. If they are identical, you've got homotopic protons and groups. So those are NMR equivalent. If they are enantiomers, now you've got enantiotopic protons that you're comparing. So those are going to be NMR equivalent. But if the structures are diastereomers, now the original two hydrogens you are questioning are diastereotopic, okay? Or protons, or excuse me, diastereotopic groups or protons. So you can have diastereotopic groups and nonetheless, they're going to be NMR non-equivalent. If they are just constitutional isomers, those are probably heterotopic type, and those are going to be NMR non-equivalent. An alternative option is to look for rotational or reflectional symmetry in the molecule. If protons or groups can be interchanged by either of these symmetry elements, then they are NMR equivalent and they will share the same NMR signal. So here's an example. Let's go through this and then I'll show you a couple more. But you can see the symmetry about the middle of the molecule. Each carbon's attached to the same things. You have a CH2 followed by a chlorine. So it's a carbon attached to two hydrogens and a chlorine on each side. And you want to know, are these two protons NMR equivalent or NMR unequivalent? And so let's test that with our deuterium replacement test. So I'm going to redraw 2 times. The first time I'm going to replace one of the hydrogens with a deuterium. And the second time I'll replace the other one. Okay, and then I'm going to compare those two structures. Before I do that, I have created a stereocenter, okay, by doing this. It was a CH2, but when I do the test, it creates a stereocenter. And so you can also do R's and S as well to help your evaluation. And so I've got the S enantiomer here and the R enantiomer there. So as I just mentioned, these are enantiomers. Formed after I did this replacement test. And so you go back to your original 2 hydrogens and you can say now that these are enantiotopic. And that means that they're NMR equivalent. Okay, let's do one more thing. Let's compare another set. Let's compare this hydrogen to that hydrogen. Okay. So I'm going to replace again and compare the structures. And I just do this for any hydrogen that I'm really having troubles questioning. Maybe it's not easy to see. Maybe it is. That's up to you. But if I go ahead and pick a different set of hydrogens to compare, I'm just going to draw it like this. Since it's a deuterium, I'll draw the deuterium in. And assume the other one's a hydrogen behind it. So I can go ahead and see there's a stereocenter formed here. So I've got the S enantiomer here and the S enantiomer there. So these are identical. And that means then that these 2 hydrogens are homotopic, which also means they're NMR equivalent. Okay, and now there's one more set that I want to just show you. Let's do the case where we have the wedge and then the dash on the other one. And so let's go ahead and draw Again, you don't have to do all these if it's easy for you to determine. I'm just showing you that there's this tool here that you can use if you struggle or if you're asked and you don't know. And so now I see I have a stereocenter. This is still going to be S. And I need a chlorine here. And so that becomes, looks S, but now it's R. And so these are enantiomers. So you can then say that these with the asterisk are enantiotopic. And they're NMR equivalent. Let me show you if you do this. Let's put these into a eclipse conformation for the last case. And if you do the other one, let's see, we're gonna, right? So if you were to compare a single structure now, and you drew those two hydrogens in as deuteriums that you're comparing on the same structure, you see the reflectional symmetry, okay? So the reflectional symmetry there. The one that's homotopic has rotational symmetry, but those are non-mirror imaged, or those are mirror imaged environments. And so you can see that those are enantiomers or enantiotopic hydrogens. So that'll tell you here that there should be then one NMR signal for this structure because they're all NMR equivalent. And so we're going to have overall you're going to have one NMR peak for this compound because they're all NMR equivalent. So that's how this test can be useful. I got some other problems here. I'll let you do that on your own, but I'll go ahead and tell you what the answers are, and then you can confirm it. I will do one more, I guess. Let's go ahead and do C. I'll let you do B and D on your own, but I'll put the right answers so that way you can see if you get the same thing. And so let's do C. C is pretty easy. If you think about the connectivity of the hydrogens, they all look pretty different, right? You have the carboxylic acid there, and then you have this other carboxylic acid over here. And those carboxylic acids are not connected to the same thing. In fact, this one's connected to a carbon that has an OH, and this one's connected to a carbon that doesn't. And so you know that they're just in different environments, so we're going to treat them differently. Those are homotopic hydrogens. If you go here, you have two different sets of hydrogens. You have one on the carbon and one on the OH. So we're going to go ahead and give those their own shape. Okay, and now the real question is, also notice here that you have a stereocenter present already in the molecule. So I'll just call it a resident stereocenter present. And if you consider what's going to happen next when you do a deuterium replacement on the CH2 carbon with those hydrogens. So if you were to question these two hydrogens when you do a deuterium replacement, you're going to create a second stereocenter that you're changing. And so basically you're creating this non-mirror imaged diastereotopic environment. And so we can look at that, and I'll just do it side by side here for you just to show you. I'm just going to draw the OH in, but then we're going to do a replacement here and compare it to the other case where you replace the other hydrogen. And you're keeping that resident stereo center fixed because it's not changing. It's fixed, it's inherent in the molecule. And now you've got diastereomers here. Okay, and so that tells you when you go back to your original two hydrogens here, that these, even though they're on the same carbon, they're diastereotopic. And so in theory, they should have their own chemical signal because they're NMR different. They're not equivalent. They each have their own signal. Each signal would integrate to one hydrogen, and it would have its own splitting. So diastereotopic hydrogens also split each other, as well as the hydrogens that are adjacent carbons. And so these geminal hydrogens get tricky when you start adding stereocenters, and it complexes the NMR a little bit. So basically for C, you've got those two diastereotopic ones. So we're going to give those different shapes. Let's go ahead and put one, let's say like this. We'll put a circle and a line through it, and then this one will put a square and a line through it. And now we count all the shapes up, and we've got 1, 2, 3, 4, 5, 6. So we should see 6 signals total in the NMR. In the NMR spectra. Okay, now hopefully those signals are all resolved. They're not overlapping, so you'd be able to see them clearly then. All right, so that's that one. What I'll do is I'll tell you what the other ones are in terms of how many signals you can see, and then I'll let you work them out on your own. So for D here, there are 5 unique NMR signals. Five. So I'll let you figure out why. If you can see it, great. And if you can't, then do the deuterium replacement test. For B, I believe there are 3 NMR signals. I'll just say 3 unique sets of hydrogens in terms of the proton NMR. Let's just write 1H NMR. Okay, so that means you have 3 peaks expected. So you can convince yourself of that, as I did, doing the deuterium replacement test, but I'm not going to work that out in this lecture. I'll let you do it and I'll give you the right answer. All right, so let's look at the NMR structure for D. All right, so this one is kind of a giveaway now, right? So I told you there was 5 unique proton signals. I'll let you convince yourself why if you have any question. So here is the NMR for structure D, and you can see here that we've got 1 signal, 2 signals, 3 signals, 4 signals and 5 signals, right? Because there's 5 unique sets of hydrogens. There should be 5 unique signals in the NMR. Each of them get their own integration. And I'll give you a clue here. So we have 11 total hydrogens. And so what's not shown is the integration. So I'll just leave that up to you. Can you figure out the integration or the integrals for each peak? And that's what I'll cover in the next video. Okay, so that's something that you can try here if I don't already have it shown. All right, so here's the structure. Once again, I've drawn in all the hydrogens. I'll let you figure out what peak is which, assign that, and then I'll be solving this later on in a different video. So I'll assign each unique signal to each set of hydrogens, A, B, C, D, and E. And then you'll kind of figure out then what the integral for each peak is. The integral is the area under the curve, but it's just a relative number of hydrogens per each peak. So for example, if you set this one at some number and there's the same number of hydrogens that give rise to this peak as there is this peak, then these two integrals are going to be the same. Okay. So it's a relative number of hydrogens that give rise to each peak. It's basically a ratio for all the different integrals in the structure. But I'll show you more in a different video. So for this one, that ends the video, and hopefully that helped you out and you enjoyed, and thank you for your time.